It went. Okay, got it. Okay,
Okay,
can the people hear me? I don't think the mic on this computer is that great, but anyway, I'll do my best to speak
So
well.
I'll reintroduce you for the remote folks.
Okay.
Here again is Eric Finster with the Infinity One category of types.
Okay, maybe I wonder if I like point this at over here. Maybe people can hear me. Not sure. Okay. Right. So I want to talk about the problem of coherent structures in type theory, which is a kind of old problem. So I'll first kind of like maybe blabber a bit at you about this problem, just with some random thoughts, and then I'll show you my sort of approach to coping with it. Really since 2000. Like if on arbitrary algebra on set. This other version of except it's missing apparently some version of higher algebra. And I want to sort of phrase what's missing in terms of the idea of a presentation. So let me start with that, which is I claim that one way to think about this is that type theory sort of gives us a theory of types, but it doesn't give us a theory of presentations of types. It doesn't give us the theory of what amount of data it takes to present a particular type. And I think that the theory of sort of presentations becomes more relevant in proof theoretic mathematics than maybe classical mathematics because of the following. Well, in sort of set theoretic mathematics, a presentation of a structure like a group or a ring or a field is something extra. It's distinct from the structure itself. It's like if I have a group, it might have some relation, some piece of data. As a relations and relations between relations. If I think of a higher algebraic structure like one category, or a group, or a ring, or a field, doesn't matter which one you think of. Every such thing should have a canonical presentation where I take all of the elements of that thing as generators, all of its relations as relations, all of the relations between relations as relations. And in higher mathematics, the structure itself is indistinguishable from its canonical presentation. They're the same thing. In fact, every coherent higher algebraic structure I know of is defined in this way. It is the collection of its presentation together with some extra closure properties. So think Kahn complexes, for example. Simplicial sets are the presentation. The fact that they're closed under lifting is the property that they have to satisfy. Quasi-categories are the same. All sort of things are like this. Okay, so in higher mathematics, presentations are fundamental. They are what higher algebra is. So in light of this fact, I claim that it's sort of natural to think that type theory should come equipped with a definition of what presentations of types are, because it's supposed to be a foundation for higher algebra. So if we can't, and you might think that presentations of types are definable in terms of types. This is the case for set theory. If I want to present notice our presentation is so much more complex, it appears that it just needs to be defined at the same time, okay? Types themselves, the fundamental objects we're studying, have this incredibly rich algebraic structure, which is just absent in set theory. And so a notion of what it means to collect all of that structure together needs to be primitive. That's my sort of, so now this has some actually precedent. I mean, when we talk about in type theory, for example, the usual way we talk about presentations of types are like inductive types, right? This is how we present inductive or co-inductive, whatever types. And so one way of doing this is to make what HoTT and Agda do, to make these inductive types sort of primitives of the language. So you have either matching constructs or something like this. In some way, the notion of inductive or co-inductive type, the notion of presentation is really primitive. There was this really nice theory that I've always been a fan of by Connor McBride a long time ago, where he said, we're going to do something slightly different. Instead of giving you fundamental operations like the data keyword and stuff like this, things that are added onto type theory, instead, he's going to give you a universe of inductive. This is the kind of thing I have in mind, except for this paper was sort of written before we knew about higher inductive types. So it only presents what I would call free types, inductive types that are freely generated. And it doesn't take into account inductively types that have relations, which is what higher inductive types are. And so the notion of presentation is incredibly simple. In fact, in his paper, he even describes it with the data type itself. But if you want to do higher inductive types, you need some notion of some faces and so on. And that notion of geometry, those relations are just not included in naive versions of presentations like this. So there's also some flexibility in what you mean by presentation. So I've been speaking at a sort of abstract level because I think that's where the sort of philosophical aspect of this lives. We need a notion of presentation. But when you actually make that concrete, there's a lot of choice. So for me, the search for semi-simplicial types is the search for one particular way of presenting types that can be presented with simplices. You could do this with cubes. You could do this with lots of different shapes. I want to do this with open-types. They may feel weird at first, but maybe I'll say one word of why I think you should do this. Well, one, they're just inductive types. For me, they're the natural continuation of inductive types into higher dimensions. Two, simplicial types, the reason they're so good in classical mathematics and cubical types is because they're But if you're talking about a foundation for higher mathematics, where you want to talk about all sorts of higher dimensional structures, you don't want the smallest collection of geometric objects. You want the largest collection of geometric objects, because you want as much flexibility as possible in expressing what kind of structures you want. So for me, moving away from the sort of combinatorial aspects of simplices seems natural when we move to a world where we work more often by induction and quotients and so on. So the plan is to go through 100% detail. I'll try at least give you an intuition. I'm going to add them to type theory, but in a slightly, in a different way. And I'll compare a little bit with some of the things we saw yesterday. So in particular, they will be defined. Okay, so I'm going to define every aspect of this definition will compute inside, and this is implemented in Agda. If we have some time later on, I'll show you how it works. So the definition, so it won't be opaque. When an open-topic type has a definition. And the equations that make open-topic types well-defined, I'm going to need a certain handful of equations to hold, I'm going to consider as added to the meta theory. Okay, so I'm going to add the equations that hold to the meta theory, exactly because if I don't, I have to prove that infinitely many, and we don't get started. Okay, and we stay where we've been for 10 years and nothing happens. We can't prove it. Okay, so I'm gonna modify the equational the equational computational aspects of Agda, and I can do this because it has rewrite rules now. So what is an open-topic type? Well, similar to what people imagine for simplicial types or cubical types or so on, it's an infinite sequence of dependent families. Which each give you a type of fillers for some geometric configuration. Okay, so and just the notion of boundary. two-dimensional things. But think of it as they're all the frames are homeomorphic to spheres after realization. They're like frames. Anyway, so you're going to have an infinite sequence of families. Once you specify the 0 cells, there'll be a type of well-formed one-dimensional boundaries for which you'll specify a type of fillers. Once you specify the type of fillers, there'll be a type of well-formed two-dimensional boundaries for which you'll give a family of two-dimensional cells, and so on. Okay, so at each point you accumulate the frames here depend on all the previous data you've given. Okay, and in fact, you can even just say right away that an opentopic type of dimension n+1 is an opentopic type of dimension n together with a map from the frames with a family specifying for every boundary a type of fillers. Okay, so that definition. So this type checks right away. It's just that so far I haven't defined what this is, right? So I need to tell you how to define boundaries, and that's where all the problems. The opentopics in arbitrarily high dimension work for simplicity. And so so just to get an intuition, so in dimension 0, we have a type, and the only opentopic dimension 0 is, it looks like this little box, and I've labeled it with X to indicate that X is an element of the 0-dimensional type that I've chosen for my opentopic type. It turns out the frames that you get are just pairs of elements, which if you use these diagrams, should be stacked on top of each other like this. X is the input. It also corresponds to this incoming line here, and Y is the output. It corresponds to the outline. And just and the boundary here is dimensions. After you've specified, you've given me a type of, if you like, arrows right here. Then I can make a whole. There's a whole collection of boundaries that look like chains of arrows, and they're drawn like this. The 0-dimensional is X, Y, and Z, F, and G. So I should have given the geometric picture as well. This is a sort of projection of just this classical picture of this X, Y, and Z. F is this arrow up here. G is this arrow down here. The H living below it is sort of this closed arrow right. Ellipses and opentopics coincide, but it's okay. And in general, an opentopic looks like this sequence of trees labeled with some lower dimensional data, and the boundary is just if the opentopic is of dimension. This one is of dimension 3. The opentopic is the first. The boundary is the first 3 things, and then the top dimensional cell is the filling stuff. Okay, so you can sort of visualize these things with pictures. So I'll sort of keep using these, but I don't have time to explain it in all the rules for constructing these because that would be the whole picture itself. Okay, so again, right. So for each opentopic type, on the slice category over frames, right? So it's an indexed monad. So an ordinary monad would just be a type constructor type to type, but this one is indexed. It's types over the boundary, and it sends it to types over the boundary. So the way you should imagine what this monad does is it takes a choice of filling families, diagrams that you can. So you choose your formed two-dimensional paper. Okay, so this is yeah. It's not quite. Yeah, it's the formal words, except everything is tree-like. So you can think of even in dimension 3. So you can sort of see that in the picture, even in higher dimensions. Everything, every cell that you pick has a kind of collection of inputs and a collection of outputs. And so if you think of this as the signature of some algebraic theory, then it's the collection of well-formed terms of that theory, if you like. Okay. In other words, trees built from these things taken as primitive expressions. But as you glue together trees in higher dimensions, the thing that's tricky about it is it affects the shape of the boundary in lower dimensions. That's what's non-trivial about this. So this, you've gone up to dimension n, you choose a collection of fillers for all the boundaries you've created so far. This monad is going to tell you, it's going to produce for you the type of pasting diagrams generated from that data. And yeah, so as an example, so in the lowest dimension, I pick, let's just do dimension 1, I pick X a type. It turns out the type of frames are just pairs of elements. So I said, and so if you picture the elements R here as living inside this relation, then this functor PD of R returns the type of pasting diagrams built from that relation, which are just linear trees in this case. Okay, so this is the monad. It's essentially the list monad, except for it categorical form. It looks like I start with a collection of fillers, which are arrows, and this functor returns for me the type of strings of arrows, which is sort of the pasting diagrams made from the arrows I've done so far. Okay. In dimension 2, you get planar trees, and in dimension 3, you get 3-dimensional trees, and so on. We'll talk again about what filling family. So I need to tell of the next dimension R. Okay, and to say what the frames after passing one dimension forward are going to be. So a frame of X extended by R, once I've added this filling family, well, it's just a frame in X, then an element of R, which I think of as the target, and a pasting diagram generated from the previous element of R. Okay, so if I'm in dimension 1, and I want to know what a 2 frame is, I choose an element U to be the target, pasting diagram combination of just the source I chose. So what did I have? I had R, S, and T, and then I picked U to be down here, and now I've created a new hole in dimension 2 for there to be a new set of fillers. Okay, so this theory is very yeah, it's generated by, again, sort of so the are just pairs of elements of the family that you chose and pasting diagrams generated from the family you chose. Okay, so what's the coherence issue with this? This all looks nice. Well, the problem is in defining this monad structure in every dimension. Okay, so you can think this an overtopic type. As I look further and further down, I have to get this monad, and this monad, the definition of the monad will in dimension n plus 1 relies on the monad in dimension n being associative. So then, if you want to finish the definition, you have to say that of the coherence problem that we've never been able to escape from, which is you get this infinite regress. If you don't have any additional help, any equations, the definition never finishes. Okay. So we're going to consider that. So my approach here is to consider that these pasting diagrams and this notion of presentation is so fundamental, and these operators are the operators describing what higher dimensional shapes look like. Okay. So those, I think, should be part of the theory. Homotopy type theory should tell you about a certain geometry that you can then use to work with and use presentation type. So there's a map operator because PD is a functor, a return operator, and a bind operator. And in the development, you really use these. That's the other thing I like about opentopes is you program with higher dimensional structures the way you do functional programming. Okay, but in order for this to work, we need these operators to have better normal forms than they ordinarily would. In other words, I'm just going to make them definitionally associative and mutable. So what that means is if I apply mu to some neutral term, so some amount of variable of mu when it doesn't compute. So what you need to have happen is you need that thing to compute into a normal form, and then you're okay. Okay, so after you do that, you get a type of presentation. So if you strictify the equations here, the definition type checks, and there's no more problem. In fact, you can do this in Agda. Okay, so that's the idea. Now I'm lying a little bit on this slide. It's always good to lie in your talks. Which is that, so this is the crux of the map. This is a monad. Okay, so these are the monads describing what higher dimensional syntax should be, and those need to be primitive. But these monads are not arbitrary. They're Cartesian polynomial monads, okay? And that actually plays a role in the definition, okay? So there's a bunch of equations that I'm not writing here having to do with implementing the fact that these monads are special, that they're Cartesian polynomial. This amounts to a kind of like algebra of positions. That's one way to say it. So all these monads are container monads or polynomial monads. And if you know what a container is, it's a type of it has a type of constructors and then type of positions. So what's but the main thing that you want to do is somehow make these monads strictly associative. Okay. So yeah, okay. So if you do this, you get the type of open-topic types for every n, and then you can use co-induction to have the type of infinite open-topic types. Okay, so that goes through the definition now. Type checks, and you're fine. But unfortunately, you have not solved the problem at all. Once you've gone to define open-topic type, the next thing you want to do is you want to say what is a map of open-topic types, and unless you have some additional equations. And this is the, I think this is the fear somehow that people have had about just doing what I'm doing here, which is brutally adjoining to type theory, a theory of presentations, because it's totally unclear if you're ever going to win this battle. Okay, so it's unclear if I will. And so, but I claim there is a natural place to stop, to sort of put a mark, to set yourself, which is that we just added the type of presentations. We should add the type theory of presentations, okay? So what do I mean by this? Well, if you were thinking semantically, open topics are a pre-sheaf category, and any pre-sheaf category has a category with family structure. That's to add a particular, so the open topic type maps of open topic institutions. In context. Stability. The universe is the open-topic type of open-topic types, together with its universal fibration. Okay? This turns out to be more convenient for a reason that I'll get to later. But if you have these two things, if you have the universe of open-topic types and maps, then you can reason about dependent open-topic types by just considering them as maps to the universe. Okay? So once you have a universal fibration, you have a notion of dependent open-topic type already. So anyway, so that's fine. So the thing that you're going to axiomatize is these four pieces of data. Okay. So in a sense, what I'm building here is a two-level type theory. but there's some important differences. Okay, the important differences are the following. So my and I think this is really way, which I find a little bit what non you have to close this universe under all the type constructors. You have to close under sigma and pi by hand, and now you have parallel universes of presentations. But why should you need two? I'm not sure. I would rather say that a non-fibrant type is a presentation of a type in the sense that I've been describing here. That's what it means to be non-fibrant. Okay, but these objects, they should be defined in terms of types themselves. The other sort of obvious disadvantage of two-level type theory is that these exotypes, you ask them to be set truncated so that you can make progress on the coherence issue, but that means you give up univalence. And that for me is actually that's actually the real problem for me. That's a deal breaker, I mean, because for me, the point of HoTT is univalence. So I can't give that up, sorry. I can't go back to the situation where we use sets to reason about homotopy types, because that's why I wanted to use HoTT in the first place, to avoid having to do that. So here, the difference is we introduce in the meta theory, because I need the meta theory to strictify these equations. We introduce this theory of presentations, but the non-fibrant types are defined in terms. It's not really the other way around. The special. What I'm saying is that I think is kind of on the right track in the sense that you need to add a theory of presentations, but you should do it in such a way that those presentations are still univalent, and that's what's happening here. So let me say a quick word. Oh, I'm going to finish. I'm going really fast. I was worried that I wouldn't go really fast, so maybe I'll have time to show you. Am I going? Does anyone have any questions? Am I going too fast? Yeah. Yeah.
Maybe I'm making a different comment that you said that the type theory, the non-fibrant types are analogous to more representation. So I feel like the representation doesn't do that. The type of types, but they don't have fibrant types.
You can't, because it collapses the two. So what I'm saying is sort of schematic. What I'm saying is like the attempt at two-level type theory is the attempt to recognize that we need some notion of presentation, but I feel that it's not quite carried out in a way that makes it in particular, you can't have this fibrant replacement. So they're not really presentations of types, and they can't be. But I think sort of that's what it's aiming at somehow. Okay, so real quick, I want to describe for you what I mean by the universe. Yeah.
Did you say the map is opposite types back to this one place?
Yes, I'll show you that later on. Yeah, so that's not a problem. You do have a fibrant replacement here. Yeah. So right. So I want to describe for you this object. So just for the semantically minded people, a little bit what I'm saying can be thought of like this. Homotopy type theory is sort of axiomatizing. Well, I'll write S for like the category of spaces, even though of course it's a general topos. Maybe I should say E or something like this. It's not necessarily a category of spaces. And then by presentation, what I mean is we need some, typically in classical mathematics, this would be encoded as a pre-sheaf category. But the whole point is we can't the base layer and the presentation layer simultaneously. So I'm axiomatizing sort of this topos over this topos. Okay? Except my axiomatization like explains what the objects here are in terms of the objects here down here, which is natural. I mean, even in the semantic setup, that's what happens. Open token types are defined in terms of previous types. Okay, but what I'm saying is you need some extra computational help in order for that to make sense. Now, this sigma x in type. And this is an infinity topos. It has an object which I'm writing as the universe of open-topic types. It's the universe in this topos. Okay, and living over it is the universal fibration in this topos, okay? Which is just the analog of this, as you'll see. Okay, so I want to describe for you explicitly what this object looks like. Okay. So remember, when I'm giving an open-topic type, I have to tell you what its zero cells are. So its zero cells are type. Okay, its zero cells are types. So that means if I look at a cell of this shape in this object, it looks like a type, a type, a type. And then x1, it needs to tell me for any two types a new type. And to the types A and B, it will assign the type of relations on A and B, because that's exactly what a one-dimensional open-topic type looks like. So in this picture right here, F will be a relation on A and B, a map from A cross B to type. And G will be a relation on B cross C. And H, well, I didn't teach you how to read these diagrams, but H has the S, so when I go up a dimension, S will be a relation on all of the things I see in its boundary. Okay, does that make sense? It's so the type of fillers in this configuration is a relation on all of its faces. So S here would have type, well, S needs to be something which, given an A, a B, a C, an F in A and B, and a G in B and C, and an H in gives me a type of filler to them. Okay, so the universe, the summary, is that the universe of types here, you can think of them as heterogeneous become relations on the previous dimensional data. Okay, that makes sense? It's a little bit, yeah, it's a little bit hard to wrap your mind around, but when you get used to it, it feels pretty natural. Okay, so that's what the universe looks like. The zero cells are types, one cells are relations, the two cells are higher dimensional relations of the shape that they live inside. Okay, yeah. Okay, so should say an element of a type A and an element of A. And an element here is a pair of a type B and an element of B. And an element here is a pair of an F and an F, which is in the relation applied to A and B, and so on. Does that make sense? So each of these things was a relation. And so the universal fibration is I pick an element of each of the things that I had below relative to the elements that I've already picked. Okay? So yeah.
So know about network.
Over this. If I wanted to say what are the actual types in this open-topic type, I would have had it, I can write it over here. I should have said that it's a sigma, oops, sigma AA, right? And sigma BB, like this, right? This would be an element in the total space of this thing, whereas I've just drawn an element of a particular fiber. So, yeah, jump away. Okay, so that's the universal fibration. So sort of open. Arbitrary types. So this is another one. Maybe I can say it a different way that'll make sort of like a category theoretic way, which is this pre-sheaf category its objects are the generic shapes, just the opitopes themselves, unlabeled. One object is just a simplex. O, that weighted on the simplex. What choice of H and F makes sense. So it's a picture. Yeah. No, these are unrelated to each other. Yeah, that's just an aspect of the way that the diagram has to be projected onto the screen, that they're sort of inside of each other, but they're unrelated. Yeah. Yeah, just by the fact that F has a relation whose output is B, and G is a relation which is output whose input is B, but otherwise they're unrelated types. Yeah. Okay, so that's what the universal fibration looks like. You have to get your head around it a little bit. It's a little tautological. I mean, it should be tautological. It's sort of the universe, but that's it. It's obitopically shaped relations and their elements. Okay, so you don't get anywhere. You can't really define this. You have great. You've made this type, but it's hard. You can't create any elements of it. But what I want to argue is that if you add this, if you add the type theory of presentations, suddenly you start to make a lot of progress. Okay. Yeah.
So we need to add some more.
Yeah, that's right. Equations that fine. So I'm really building an so first you get a lot of definitions. So once you, and this actually only depends on having opitopic types around, right? So once I have opitopic types, I know how to define an infinity groupoid or an infinity one category. I can even define infinity operats, monoids, and groups. It actually turns out, and this is what I was saying about why I like opitopes as a general theory of presentations, because you can define lots of other structures like infinity n categories. With some modifications, you can do symmetric monoidal infinity n categories. I have some sort of putting that on the back burner for now, but you get a lot of objects that you can describe with this class of presentations. Whereas if you add semi-simplicial types, you probably only get the first two, and the rest you have to construct by hand internally. So all these things are definable, so you get a lot of definitions. Definitions aren't interesting. I mean, because definitions are just definitions. What's interesting is theorems and constructions. So can you do anything with these? And the answer turns out to be yes, you can do it. Structure can be defined in terms of the sum and the pi and the base theory. So you don't need to add more coherences. You can now close this under some constructions. Okay, so this is an example of now that opitopic types compute, the fact that they're defined. Okay, so you can you can to any type x, like I was saying, you expect any type x to give rise to the canonical presentation of x. So I take all its points, all its lines, all its simplices, all its opitopically shaped identity types, and I should be able to define an opitopic type whose n cells are the equalities that exist in a just start writing down chains of types, you won't get very far. But it turns out there is a natural and simple definition which does it all at once, and so this is fine. You can define the join of two homotopic types. So this is like a classical construction in homotopy theory. Well, we have the join of types. The join of homotopic types is you take two homotopic types, you glue a one cell from every point to every other point of the two types, and then you need to add infinitely many higher cells that make all the relevant triangles commute. So if you have an arrow on this side, here, then I definitely want a two cell. I need to glue in an infinite amount of data in order to sort of join these two things. Join the presentations, not the types, but the presentations in a coherent way. But it turns out that's definable as well. And a nice thing about that is that means you can give a definition of what a limit and a co-limit of infinity categories is, because this is defined just in terms of joining with the arrow. So you get out of this not just the definition of an infinity category, but some constructions. And then there's some theorems you can prove. So last year we had this paper, which was written in a slightly different setup, but along the same ideas, where we showed that actually the definition, you get a definition of infinity groupoid, and you can forget out the objects of your infinity groupoid, and that you get a type, and that map is an equivalence. So every map admits an infinity groupoid structure, and that structure is unique. So that you can prove. And again, a priori, from just the CWF structure, it's not clear that you should be able to do something like that. So I have a student. So which is that let's consider this universe. Particular shape, then I see a bunch of types, a bunch of relations between them, and a bunch of relations depending on all the previous data. Okay, and so let me say that this type, this element of the universe, I'm going to say it's a fibrant relation. If whenever I look up in the universal fibration, so whenever I pick a bunch of elements living over it in the shape of a pacing diagram, that the type of output elements living over the rest of the diagram is contractible. Okay, so this is a natural notion of fibrancy for homotopes, right? So I can look inside the universe. Living over it, sub V. Is it true that the type of output, the composites and witnesses that it's composite is contractible? In other words, does it have unique composites? And this condition defines a subtype of the universe. So inside this universal fibration, O sub U and O sub V, I've just described for you a condition that singles out. In fact, this is even an internal proposition on the universe. And so this object, it could be defined this way, but I don't define it. So it's fibrant types in the universe. So this is my definition of the infinity one category of spaces. Okay? That's the underlying data. And let's just check that this makes sense. So I mean, the main thing to check, okay, so the zero cells in this object, we've already said, the zero cells are types. Okay. I is a type, and let me write it as capital F, is a relation F from X cross Y type. And the condition says that if I look at the input, the type of output is contractible. So that says that if I have an X, for any X, the type of Y in Y, and a pair of f of Y is contractible. But the type of such relations is just equivalent to the type of functions from X to Y, because it's a one-sided. We saw that. I think we saw this. Did we say that with the one-sided? So a relation like this just says in dimension 1 that it's a functional relation. Okay, so I claim that the type of 1 cells in this object is just equivalent to the type of functions from X to Y. And if you work out what the higher relations say, they're going to say something like you have a witness that that an element A maps to an element of B, and a witness that B maps to C. You need relations that these things compose. Okay, so I claim this is an extremely natural way to describe the infinity 1 category of types as a sub-object of this category of this type of presentations. And the theorem is that this is an infinity 1 category. So what do you have to, let me just say what you have to do to prove this. You have to say that if you have so suppose that I'm looking in the universe and I just have some F and G, which are fibrant relations, then I need to show that there's a so this can be done. So that's the theorem that you can do. So this is actually, I would say, I have to give a guess, maybe 85% implemented in AGA. I don't think there's any obstruction to finishing the proof. So I think we'll soon have the proof that this is an infinity 1 category. It's only not done because of Benedict. He kept making me go out to eat. It easily could have been done this weekend. Benedict's fault. Yeah. So just come back to finish, is that it has a kind of completeness to it. You sort of guess for very general reasons that you could do anything with it that you could do with classical mathematics. I think in practical terms this still needs to be justified, but let's grant theoretically that you can sort of do that. So because of that, it has like the sort of guarantee that it's probably, you could probably do everything. And we don't know this for sure, but you probably. Here, the game is you don't know what we can do. Okay, I've given is how much can more at some point? I don't know. Can't answer the question. The only way I really know to do this is to start trying to prove theorems and see how strong this theory is. And so that's the sort of example that I want to give today. And I think I'll stop here. So yeah, that's a good question. So I mean, if I look in a standard pre-sheaf model, you can do the bias-Dillon slice construction in any pre-sheaf in any topos, and it's strictly associative. So the only possible thing that could go wrong with this is for some reason the translation has some kind of thing that you need to strictify to get it correct. But with the bias-Dillon construction in classical mathematics, so if you take semantic to type theory in one topos, it is associative and mutable. I've only to check that these things really so you have some choice, because if I consider these primitives, I can map them to anything I want. So I think this to me, this kind of obviously has models because this construction in classical mathematics is associative and mutable. So I don't think there's really a serious problem with the model theory here. No. About the? Yeah.
So you have new adaptations.
Right. Also a good question. I believe the answer is yes, but I don't have a formal proof. So the monad, strict defining the monad laws, this has been done before. There have been a couple of attempts at doing this kind of thing. In general, structure. So these are, I think that's going to operators, and I'm not sure in the form it is the optimal form to do that kind of investigation, but eventually, definitely, I would like to work out like a specific, what is the algebraic theory that one needs to interpret this, and then check it. So that has to be done, but I have to do that.
Can I ask about this string types and utility points?
Yeah.
So
Yeah.
I think you said that the map going up there just forgetting all the structure and just taking the base type out.
Yep.
I assume the other ones taking the quality types.
That's right. Yeah.
So is that theorem really the same if you define to infinity group with that all the extra structure you gave was just it?
Exactly. And you should think of it like the notion of infinity group is defined in terms of given a space of pillars, there's a contractible output. And the fundamental theorem of homotopy type theory tells you that any such thing is an equality type. And so essentially this theorem is a souped up version of the fundamental theorem of identity types, which does a little bit more than identify that it is the identity type, but it also shows that all the composition laws are the composition laws of the identity type. But in principle,
So the reasons that you gave for using opensource seem like mostly convenience based. So do you think that you could, not that you should, but that you could do this with a similar?
that's a really good question. So yeah, so I think you could dig out, I'm not sure why we never tried this. I think you could dig out the various presentations that people have, right? So people have, and strictify their equations and arrive at something. That's why I say I think there's some leeway in doing that. One thing that's different and people have written these out actually for the face relations for opotopes. But notice when I set this up, I didn't strictify the equations of this category. But for simplicial types, I don't know what other option there is. Do you see what I mean? The only thing that I know to strictify for simplicial types is the simplicial relations. Right? This is the thing that happens. Well, I mean, but these ones are already okay, but what happens is when you have threefold relations, right? You need them to you need some coherence between iterated applications. In other words, you need but for opotopes, there's enough. You see what I mean? So you could do this. I don't know what kind of theory it is. I don't know what kind of theory it is. It's not at all clear to me. So there's one more thing that I didn't say, which is that the other advantage is these pasting diagrams here. They are defined by an inductive type. So all of these proofs, they go by induction on the structure of the pasting diagram. I have a pasting diagram, and literally I pattern match on the pieces of the pasting diagram and find it. There's nothing to replace that with simplicity. You won't have an inductive type of simplicities. The thing that parameterizes simplicity is just a natural number n, right? You need something else. You need these relations, but they won't be induction. So I don't know what that theory would look like, even though in principle you could start trying to see what it is. And I think something could be made to work.
Possible that you could, this for speculation, is it possible you could define like semi-simplicial types in terms of optimal?
That's already a consequence of what we've done.
Does that?
So I mean, because
I guess it's the problems more that if you wanted to find some visual type without assuming the optimal,
right,
just assuming something else.
right. So we already have a notion of
You can
infinity
make
one.
like a simplicial type, just.
That's right. So you already have a definition of simplicial type because you have a definition in infinity one category. I showed you this theorem that you can construct from it an ordinary category, an infinity one category. That's straightforward. You can construct from delta defined as is an infinity one category and look at maps of the universe and this gives you simplicial type. So as soon as you so that's already a definable thing. It's there. Maybe I should have put it on the list. Yeah.
The new definition and category.
Yes. Yes.
So that in particular types as its core.
Right, exactly. And this is again provable because if you look at what it means to be invertible here, you'll get exactly these two-sided relations that we're talking about before, and those are equivalent to equivalences. And okay, let's stop here. So if I can leave. Oh, I lost. I always keep losing my mouse.